Happy Postgres Day. Thanks for joining me for a very important event, talk about Postgres and real-time event modeling. Back when I was just getting into geospatial in the late 90s, web technology for maps was super primitive. But there was this fancy thing called Java, which had been around a little longer. And there were some cool map displays, JViews and BBN OpenMap, which felt promising. The idea of a Java-based map was exciting to me because Java had this thing called remote method invocation that sort of set my mind spinning because it seemed like a wonderful trick to sync up a bunch of map displays. In retrospect, from a technology point of view, it was all pretty ridiculous. But as a concept, you make a change here, and then it's immediately visible there. If the promise of digital mapping made anything, it meant a shared and real-time view of the state of the underlying system. Like the idea of a shared map view really reached deep into my subconscious and tweaked something. And frankly, it's a little odd that most of our mapping UIs don't bother to display the state of the underlying data unless a map refresh is triggered. Like, why do we consider that acceptable? And it's probably an echo of the state of things like 30 years ago, when running a GIS system meant running against your own static local copy of the data, but there's no need to, so there was no need to refresh the screen. Like the only way the data was going to change was if you personally changed it. But if the data are in a database, if they're online in a shared system, well, then they can be changing all the time. And having a map view that's just the last time you refresh the map, that starts to feel really wrong. Now, lately, I've been watching Tom McWright building Placemark.io with some jealousy as he uses his Jedi powers of product design and full-stack programming and awesome JavaScript knowledge to create really the most perfect instance of something I've dreamt about for years. And to assuage that sense of jealousy, I've taken to building out the primitive pieces of a Postgres-centric take on live data in general and live data on the map in particular, using the tools that Postgres makes available to me. If you're interested in trying out the live demo, you can visit the following URL and let this serve as a reminder to me to put it into the chat at this point in the video. http://s3.cleverelephant.ca/mo/moving-objects.html. So rather than building this demo up from scratch, I'd like to show you what it does first, and then talk about the parts that make it work. So first of all, note that we have two windows all showing the same thing. There's multiple moving object dots. The motion in this demo is provided by the user, although like a real world moving object system would probably get the location updates from some kind of a GPS or other location sensor in a physical object. So I got these little buttons here to generate movement. When I click on a button, the object moves in the direction that I click. And you can see that both windows are synchronized. So I'm clicking over here in the window on the left, and the window on the right is following along. It doesn't matter which window you move the object from. They all move the same. They're all being kept in sync. I can even move them from my phone. Since the web page there, it's just a simple web page. It really doesn't care what kind of device it's running on. Now, this system has two classes of objects in it. It's got the moving objects themselves, little colored dots, and a collection of geofences. These are these blue polygonal areas that we want to monitor for exits and entrances. And if an object wanders into a geofence, every watching map gets updated. So you got the one on the left, one on the right, both are updated. And when an object wanders out, same story. They're all being updated in the same way. They're all being updated from the same central state that the system is storing in the database. So the map windows are reflecting this underlying shared state. And that shared state lives in the database. So that means I can also change the shared state using any database tool. So I can go and update the database state of the red moving object now. I'm going to go update objects, set geog equal to, I'm going to take it all the way to the west. And I'm only going to do it where the for the red object. And when I commit this to the database, the shared state will be transmitted out to the clients, and the red dot hops to its new location. The beauty of using database state is that a moving object system can be manipulated using any tool. That's the cool part. I don't need a fancy web UI or API to support changes. I can just do it using a standard database tool. So suppose I want to add a new geofence to my web app. I just go and grab a handy tool for manipulating polygon layers in my database. Let's see, put it into edit mode. Add a new geofence. Give it a name. Okay, now it's in my local context in QGIS. When I hit save, it goes to the database and thus gets transmitted out to the watching clients. And that's a real live geofence. It just as much as any of the other objects does. It's going to do the same things as the pre-existing objects. It'll notice when things go into it. It'll notice when things go out of it. And again, like I added it using QGIS. I could remove it using QGIS. I can remove it using any database tool I want. Delete from geofences where label is new. And it goes away. So that geofence can be added with any database tool or removed with any database tool. I can also use my generic tool, QGIS, in this case, to visualize any of the entities in my system. So I'm already visualizing the geofences. I'm already visualizing the object locations. I'm also visualizing the object history. This is a table which is filled up on demand as the objects move around. So I've got the long windy road of my little red object, my green and my purple objects. Haven't moved anywhere yet, but if I give them a little bit of history, they'll show up in the history table automatically. And I could just as easily hook up a dashboarding tool or a BI tool to the database and have all the powers of those tools apply to my moving object system. So by building the system inside the database, I not only get the system itself, which is nice, but I also get all the capabilities of any other database tool that I choose to bring to the party. I really love the idea of the database as the integration point for bringing together a whole bunch of different software, because it kind of fulfills the old programming promise of just stringing together some components to build an app. Any component that can speak to the database can participate in this moving object model. Anyways, that demo was a very simple, very small example of a moving object tracker. It's a little bespoke, for sure. It was my first attempt, but it proved some important things to me. First, it proved that a simple database model could represent the problem and answer the kinds of queries that would be asked over and over again. Second, it showed that it was possible to write active data logic that would fire off when the data state changed. This is really important for wiring in generic database clients to an active moving object system. The moving object logic has to work in response to the kinds of ordinary data manipulation that generic tools do. And third, it showed me that it was possible to push database state out to clients in real time. This required some fresh development, but it turned out to be, like the work on PG-TileServe and PG-FeatureServe, a relatively small amount of fresh development, thanks to the facilities that are already built into Postgres. So first of all, what are the pieces you need to make a moving objects tracker? Regardless if you're modeling the problem out in some programming language or in the database, you're going to end up with the same basic entities. You're going to have some kind of object table. It'll have the location of the object. It'll have some kind of unique identifier. You'll have some kind of timestamp with the most recent observation. It might have some other domain-specific properties, like an altitude or velocity, like for a plane, or like a big status array for a garbage truck. It might look like this. I'm still going back and forth between having the columns of the object table be the properties, or to try to abstract them away into some sort of JSON column. So I have a props column here in JSON, but I also have a color column, which is just a standard text column. The fences column is something special, and we'll see the trigger that applies this logic later, but it's worth explaining now. So geofences are polygonal areas of interest that sit in a moving objects model. Now, a simple event model might just check, like each time the object moves, to see if it's inside the fence, and then add that to the event. So you'd get a movement, I'm in a fence, over and over and over again. A lot of applications are less interested in the current inside or outside state of objects relative to fences, and more interested in that transition moment. Can the system raise an alert when an object first enters a fence, and then again when it leaves a fence? So the fences attribute on the objects table allows me to create those kind of events. By recording the previous state of the object with respect to what fences it's in, the system can compare the current state to the previous state and raise events when the state changes. The geofences table itself, in this example, is trivially simple. It's just a unique key, a polygon, some text, and a timestamp to keep track of the creation time. Because this is a database-centric design, it also makes sense to not only keep track of current state, but also store the historic state of the system. And for that, I added a history table. Objects, the history table is really just a copy of the objects table with its own unique key. And the history table is one of those pieces of the model that we need our active system in the database to keep up to date, even if the third-party applications only modify the state of the objects table independently. So they never update the history table. That happens inside the state automatically when changes are applied to the objects. So I've mentioned the idea of an active system a number of times. And so what am I talking about when I say active system? An active system is one that fires off actions in response to changes in the system state. In the case of our moving object system, the primary change of state is the movement of one of the objects, and that change of state fires off a number of actions. The new state is immediately recorded in the history table, so we have a retrospective record of the state of the system at all past times. The new location is compared to the geofences and compared to the previous state to flag any entering or leaving events that have happened. And then the new location and any geofence events are bundled into a JSON payload and transmitted to any clients listening to updates. Now, before we get to this third action, which is kind of novel, pushing payloads out to awaiting clients, I want to show some of the machinery inside the database that is making this happen. This all works because Postgres supports triggers. So what's a trigger? A trigger ties a function, which can contain any logic it wants, to a change in a table, an insert, an update, or a delete of data. But this is exactly what we need. Like as our objects move, we're repeatedly running an update on the objects table to change the location. And if we fire off some logic every time that happens, we have an active system. So a trigger consists of two pieces, the trigger function that defines the logic which gets run, and the trigger definition that binds the function to the table and the particular events, inserts, updates, or deletes that fire the trigger. So here's a trigger function. This is one that's used in the geofences table. This is about the simplest possible trigger function. All it's doing is binding up some static information, the payload type, the layer name, the change type into a JSON object. And then the object is sent off as a notification to listening clients, and we'll talk more about that later. And this function is actually being deliberately a little bit clever. It makes no reference to the table name it's going to be bound to, no name to the change types that it's handling. So it can be used on any table and send out a notification for any change that happens to the table. So regardless of whether it's an insert, an update, or delete, when this trigger is fired, it'll fire off a payload that includes the information about what table the event happened on and what kind of event it was. And we use two constants that exist only in trigger functions when doing this. The TG table name is a magic constant, so it's the name of the table the function's bound to, and the TG op, and that's the name of the operation which is fired when the trigger started. So to bind the function to the table, we just create the trigger like this. Create trigger, trigger name, then we say what events it's going to be tied to, what table it's going to be attached to. Then we say either fire the trigger once for each statement or once for each event. Or sorry, once for each row. This one is being fired once for each statement. So it'll fire, even if you're updating 100 rows, it'll fire once for that one update. On the other hand, a row-based trigger, if you fired it for 100 rows, it would fire off 100 times. So rather than walk through the more complicated triggers that run the geofence checks and the events creation, I'd like to now talk about the last step in this layer change function, because it's also the last step in the object update trigger, and it's the key to the whole moving object web page demonstration that I started with. So at the end of the layer change function, I call the PG notify function. This is a system function in Postgres. PG notify is the functional equivalent of the Postgres notify command. The notify command places a payload, a string payload, into a pub sub channel. Then any clients that have run the listen command for that channel will immediately receive the payload when it's posted. So I want to show this base functionality in action, just to take away some of the sense of magic in the later stages as we push the notification further up the stack and up to the clients. Okay, so this is a small demo. I have one terminal with PSQL command line open, and I've got two terminals that are going to be running a little custom database client. All it does is connect, and then it runs the listen command on the channel of your choice, which in this case I've called channel. And then whenever it receives a notification, it prints out the payload. So I've got two little clients running. I'm going to send some friendly text in here. I'm going to notify channel. I'm going to say hi there. And you can see they both got the message at the same time. I'm going to say hi there again. So this is all fine. We can send messages. They get them immediately, right? This is not a polling situation where the client is constantly asking the server if it has something new. This is a notification coming from the server side when the message happens. And notice they're coming in simultaneously. So we can send arbitrary text out to clients, but you know that's what's better than arbitrary text? A billion arbitrary texts. And what's better than that? Arbitrary JSON. And Postgres has some lovely facilities to generate JSON. So suppose we have a simple table of people, like that. And it's got some data in it, 2 rows. It's really easy both to turn this stuff into JSON, so you're like to JSON, like that. And then since it's been converted into JSON, it's also easy to send it to the messaging bus. You can just run PG notify. What channel do we want to send it to? The channel name channel. What do we want to send? This little JSON fragment. We're only going to send one of them. Let's send this one. So now we're sending JSON across the notification bus. And we can go even further than that, right? We can bring in a little bit of this stuff. So we talked about having a layer change function that doesn't care what the name of the table is or what the column names are. It just sends the change information out to the clients as a payload with a PG notify. Well, there's a function that does that. We're just going to pop this guy into the database, and then we'll bind it using create trigger. We'll bind it to the insert, the update, and the delete methods on the people table. So now we're in good shape. So now we can add new data, insert into people values, John is 66. So I got a new row in, and also all my listening clients have received the fact that there's been a new insert on the people table. So there you go. Very simple. This is like the Postgres side of the problem. Changes produce events that go on to the Postgres listen notify bus. Okay, we're almost there. We have a data model for moving objects, right? We've made that model active by tying triggers to the tables that are updated as the objects move. So each time an object moves, we add that to the history table. We check to see if it's entering or leaving the geofences, and then we notify clients of the move. And that notification is going out on the Postgres pub subsystem via a call to PG notify. So how do we get that notification out to a web client? Postgres notifications are sent out to Postgres clients. It is That's clients that are connecting using the Postgres client-server protocol on port 5432. They're not sent to web clients. Web clients don't talk directly to the database. So is there an analog to the Postgres pub subsystem in the web technology ecosystem that we can use to propagate the Postgres notification out to web clients? And there is indeed. It's called the WebSocket. What we need is a little program that connects to Postgres and starts listening on a channel. And when it receives a database notification, it takes the payload off that channel and passes it along to any web clients listening on a WebSocket. And to do that, I give you PG Event Serve. So PG Event Serve, it's another microservice in the spirit of PG Tile Serve and PG Feature Serve. It's single purpose. It exposes capabilities from the database onto the web with a minimal amount of code. It binds to a URL on the outside so that web clients have a place to get at it, and to a database capability on the inside. It's written in Go to allow for easy multi-platform fat binaries with no extra dependencies required, all one easy install. And all PG Event Serve does is take a URL of the form, WS, WebSocket, // the host that the service is running on, /listen, and then the channel name. Any message sent to that channel by the database will in turn be sent to the client via the WebSocket. Not only that, multiple clients can connect to the same URL, and they all share the same underlying database connection, so there's no database connection penalty to servicing a lot of web clients using PG Event Serve. They all sit on one connection. All right, so we have the server side. How does a web client connect? The minimal, like this is the smallest I could write, the minimal JavaScript implementation on the client side might look like this. We define a function that sets up a new WebSocket object, and then on that WebSocket object, the onMessage method, we set up another function that does something. In this case, the something is just logging the data to the console log. This is like the most primitive JavaScript client you could possibly write. Now, obviously, you can be a lot more clever than that. You can put a lot more logic into that onMessage method. So, for example, the PG Event Serve program itself ships with a very small JavaScript WebSocket listener that lets you listen to different channels and see the payloads directly in the UI. And I'll show that now. Okay, so for this demo, I've downloaded and started up PG Event Serve in this window. I've started it in debug mode, so we can see every request and every notification it handles. I also pointed a browser here at the Event Serve homepage, which gives a simple UI for monitoring what's coming through the various channels. In fact, I've opened up two browsers to the same Event Serve, because the whole point of this is that multiple clients are notified simultaneously of state changes on the model. And finally, I have a PSQL terminal down here, which is where I'm going to send the messages from. So first, I get both my browser clients listening via PG Event Serve. I'm going to listen to the channel, which is the one we used for a previous demo. So I get them both listening to the same one. You can see that when I connect on the one side, it sets up a WebSocket, and then I connect a second one. Now I've got two WebSockets running, open and running. And now I can send a notification, notify a channel. And we're going to say, hi there. Boom. Notice they both get the message. We've got the three things that go on. Like first, it notices that there's been notified that's been sent to the database side. So it takes that and walks over to the web side and sends that message out to WebSocket 1. Same message out to WebSocket 2. So I can also listen to multiple channels from the same client. So for example, if I'm going to add another client, I'm going to add happy here. Add a second client to this channel. Boom. So now we've got two windows listening to the happy database channel. So we've got a new database connection, which is listening to happy. And I can notify the happy channel, I am happy. And you can see that the listener for happy picks up the message, the listener for channel does not. These two are very separate things. And we've still got the data update trigger hanging around on my people table. So like if I add a record into people, it's going to trigger that function, which is going to take a JSON copy of the information and pass it out to the channel, boom, like that. And you can see that not only do we get the fact we have a layer change on the people table, that it was an insert, we can get the contents of the new record, that it was an insert, so there's nothing happening on the old record. And it might be like tempting to architect a system with lots of different channels for different things, like one channel for this, one channel for that. But note that it does take one WebSocket on each client for each channel. So it feels like it might get a bit brittle if you get lots and lots of different WebSockets open for different purposes. Fortunately, PG Event Server only actually requires one database connection per channel. So multiple channels, multiple clients on a channel does not lead to multiple database connections, but does require one database connection per channel. So back to the moving object system. How does it work? So now I've talked about all the parts. Let's look at them all together at once. The architecture is really very simple. The web UI that I showed you at the very beginning of the talk, the web UI shows the objects on a map and provides buttons to click to initiate a move of any of those objects. PG Feature Serve exposes a server-side function that accepts new coordinates for objects and updates the objects table appropriately. So here we're getting this update on the objects table, not directly moving the objects in the web client. All we're doing is updating the objects table. Then we have triggers in the objects table that fire to fill in the history table and to send the notification via the Postgres listen notify bus. PG Event Serve picks up the notification on the listen notify bus, translates that payload into a message on the WebSockets connection, and sends it out to all the listening clients. Now the web UI of each client gets that message, parses the JSON, and updates the location of the object on the map, and the cycle is complete, and all the maps are up to date with the latest status. So when you click that move button on your map interface, it doesn't actually directly move the object. What it does is it sends an update down to the database, which updates the objects table, which creates an event, comes back to event serve, and then finally that event gets back to the map UI and the object moves, and not just in your interface, but in every interface which is watching via the event server. So maybe you're wondering how far this can scale. So not infinitely. So, multiple event serve instances could run off the same Postgres backend. So pretty sure a lot of clients could be supported. The number of moving objects would seem to be a somewhat limiting step. Certainly something would have to be done to batch together movement notifications as a number of objects climbs. And then the question of like table index maintenance maybe needs some investigation. Like small tables under high update loads have some pretty specific maintenance needs. But to at least show a medium-sized scenario, I built a movement generator that can produce an arbitrary number of parallel updates to the database to simulate larger numbers of objects. So before I go, I want to show you the world map with 100 oriented markers representing planes, with the movement generator pumping out 100 updates per second. So one movement per second, approximately. There's some randomness thrown in there. One movement per second for each airplane. It's kind of mesmerizing, really. But you're not limited to moving objects. You can do any kind of notification you want using PG Event Serve. It's not just for spatial problems. It's not just for moving objects. If you have an application where the live state is important for business purposes, multiple people are monitoring that state at once, PG Event Serve and an active database model, that might be the right thing for you. Take a look.